Hi everyone, welcome back. Today we're going to look at our fourth review topic, which is very similar actually to our third review topic. So we're going to be looking at real world rate graphs. So again, these real world problems, they usually start with a big paragraph explaining what's going on, but then instead of being given a function for the rate, we're going to be given a graph that shows a rate. And then we're going to be answering questions from that. So let's get started. We have two to get through for today's video. Okay, the first question that we're going to take a look at tonight is 2010, number 3. And 2010, they still had 3 questions with calculator and 3 without. And so number 3 here is still a graphing calculator question. And so this is with calculator. All right, so let's take a look at this. It says there are 700 people in line for a popular amusement park ride when the ride begins operating in the morning. Once it begins operation, the ride accepts passengers until the park closes 8 hours later. While there is a line, people move onto the ride at a rate of 800 people per hour. The graph above shows the rate, R of t, at which the people arrive at the ride throughout the day. Time t is measured in hours from the time the ride begins operation. Okay, so part A says how many people arrive at the ride between t equals 0 and t equals 3. Show the computations that lead to your answer. Okay, so the question is asking us specifically how many people arrive at the ride. So a quantity of people who arrive. All right, well, go look back in that long paragraph we just read. And where is it giving us information about people arriving? And I would say that right here it says the graph shows the rate, R of t, at which people arrive. So, and if I look here, the graph is measured in people per hour, which is a rate. So if I want to find the total number of people who arrive from 0 to 3, it sounds to me like I'm doing the integral from 0 to 3 of R of t dt. Okay, so how do I do that from a graph where I do not know the equation? And hopefully you're saying that's area under the curve. So I'm looking from 0 to 3. Okay, so from here to here, I'm looking to find the area of all of this. So I have to kind of figure out what shapes I have. And if I break this down right at 2, I would say that I have 2 trapezoids, one from 0 to 2 and one from 2 to 3. Okay, so I'm going to go ahead and do the formula for a trapezoid, so I'll first do the one from 0 to 2. 1/2 times the height of that trapezoid would be 2, times base 1 plus base 2. Well, my 2 bases here would be 1,000 and 1,200. So 1,000 plus 1,200. Okay, so that's the first trapezoid. And now I have this other trapezoid from 2 to 3. So 1/2, this time my height is only 1 because it's just from 2 to 3. And my 2 bases are 1,200 and 800. So 1,200 plus 800. All right, I am allowed to use a calculator, so we can go ahead and enter that in and get an answer. Okay, and I get an answer of 3,200 people. All right, so 3,200 people arrive between t equals 0 and t equals 3. All right, let's move on to part B. Okay, part B says, is the number of people waiting in line to get on the ride increasing or decreasing between time t equals 2 and t equals 3? Justify your answer. All right, so let's look at what's happening in the graph between t equals 2 and t equals 3. So that is this part right here of the graph. All right, now, the question is the number of people waiting in line increasing or decreasing? All right, well, there's 2 different factors to keep in mind. There's one, which is what this graph shows, and that's your R of t. That's the rate that people are arriving at the ride. But if you read the question carefully, there's another rate that's in the problem. And that other rate is the rate at which they are getting onto the ride. Oops, I crossed that out, I didn't mean to. So the rate at which they are moving onto the ride is constantly, I did it again, 800 people per hour. So the idea is you can kind of understand this concept, right? You've all been to an amusement park probably and waited in line for a roller coaster. So, or just a ride in general. So if the number of people who are getting on the ride is smaller than the number of people who are arriving at the ride, would we say our line is getting larger or smaller? And I hope you would agree that the line would be getting longer. If the number of people getting on the ride is bigger than the number of people arriving, then I think you would agree that the line would be getting shorter. So think that through again and make sure you understand what I just said. So let's compare, okay, the number of people who are moving onto the ride, okay, which is 800 people per hour, and the number of people who are arriving at the ride between 2 and 3. So if I look here between 2 and 3, the number of people arriving is always bigger than 800. Okay, so I would say R of T is greater than 800 between T equals 2 and T equals 3. And because of that, the line is getting longer. Okay, because the number of people who are getting onto the ride is that 800 people per hour. The number of people arriving between T equals 2 and T equals 3 is always larger than 800. Therefore, the line is getting longer and longer between time T equals 2 and T equals 3. Okay, part C says, at what time T is the line for the ride the longest? How many people are in line at that time? We've looked at problems like this last time, even in the video last time, where we're talking about the gravel removal and the gravel processing and gravel that's arriving. It's the same kind of idea here. The concept is that we want to find out when the line is the longest. Well, we have to understand this idea that we were just talking about. That we want to find the time or times for which the rate of arrival is equal to the rate of ride movement, maybe? I don't know what to call it, but that's the people getting on the ride, okay? So when is the rate of arrival equal to the rate of ride movement? Well, I know the rate of ride movement, it says, is constant, 800 people per hour. So when is R of T equal to 800? And so if I look here, R of T is equal to 800 only at T equals 3 hours. So the idea now is to find out, is that the maximum? And how many people are in the line at that time? Well, take a look. Does my rate at that time switch from positive to negative? And I would say absolutely that before T equals 3, the rate is above that, and after that, the rate is below that. And we talked about when the rate of people arriving is bigger than the rate of people moving on the ride, that we will have an increase in the line. And then as the number of people arriving is smaller than the rate of people getting on the ride, then for all of these values, you will have a shorter and shorter line. Okay, so if I wanted to summarize what I just said, I would say that R of T is greater than 800 for T values between 0 and 3, and R of T is less than 800 when, so for T between 3 and 8, okay? Therefore, maximum line at T equals 3. Okay, so that answers the first part of the question. Now the second part says how many people are in the line at that time. Okay, so we need to find the exact number of people in the line at that time. So I'm going to kind of work up here just so I have room. So it says here that I start off with 700 people at the very beginning when the ride begins. So I'm going to start with 700. Then I'm going to add on the number of people from 0 to 3, which I already found in part A was 3,200. Now, That's how many people arrived. But don't forget that you have to take away the number of people who actually got on the ride. And that's where this 800 people per hour. So I'm going to subtract away the 800 people times 3 hours that the ride has been in operation. And if I type that in my calculator, I should get that I have 1,500 total people in the line at time t equals 3 hours. All right, let's move on to the last question for this problem. Okay, part D says, write but do not solve an equation involving an integral expression of r whose solution gives the earliest time t at which there is no longer a line for the ride. Okay, so we just talked about actually in that part C figuring out how many people are in the ride, and specifically are in the line, and specifically we were finding out how many people were in the line at time t equals 3. But we're going to use that same idea, okay? We want the number of people in the line at any time t, okay? So how are we going to find that? And basically what we want to show is that the number of people in line, we need it to be 0. So there's no longer a line. That would mean the number of people in line would be 0. So what we need to do is write an expression for the number of people in line. What we said as we worked through what we did before, we got the 700. That's how many people started the day. Then we added 3,200 in part C. Where did that 3,200 come from? Well, if you remember, that was the integral from 0 to 3 of the rate of r of t. Well, in this time, if we want to find the time t, at any time t, how many people are in the line, I would do the integral from 0 to t of r of t dt. And last thing I had to do was subtract away the number of people who were getting on the ride per hour. So I had to subtract away that 800 times the number of hours. And that is the full expression for the number of people in the line at any time t. And so 700 plus the integral from 0 to t of r of t dt minus 800 times t, and we want that to equal 0. And so that is the expression that I'd have to write, the equation I'd write in order to solve part D. Okay, so make sure you understand every part of that and that you feel good about it. And then we're going to go ahead and move on to the second question. Okay, 2006 number 2, and again this is a with calculator question. So we really didn't need to use our calculator very much for that 2010 number 3, but we will need to use it for this one. Okay, so it says at an intersection in Thomasville, Oregon, cars turn left at a rate of L of t equals 60 square root t sine squared of t over 3. Cars per hour over the time interval 0 to 18 hours. The graph of L of t is shown above. So this one actually is kind of, they're giving you two things. They're giving you the graph, and they're also giving you the equation. All right, so it's kind of a combo between what we did last time and this video here. Part A says, to the nearest whole number, find the total number of cars turning left at the intersection over the time interval 0 to 18 hours. Okay, so I'm going to ask you right now to pause your video and write an integral expression to find the total number of cars. Why did I know I was doing an integral expression? Well, because this right here, L of t that they gave us, was a rate of cars per hour. If I want just the total number of cars, I have to do the integral of the rate to get the quantity. So I want you to go ahead, pause the video, write the integral expression, type it in your calculator, and come back to me and see if we agree. Okay, so what you should have on your paper should look something like this. The integral from 0 to 18, that's start to finish, of the rate, L of t dt, is equal to, and then I just typed this in my calculator using this as what I was entering in for L of t, and then I ended up with 1,658 rounded to the nearest whole number, which is what they asked for right here. All right, let's move on to part B. Okay, part B says traffic engineers will consider turn restrictions when the rate of people turning left is greater than or equal to 150 cars per hour. Find all values of t for which L of t is greater than or equal to 150 and compute the average value of L over this time interval indicate units of measure. Okay, so let's take a look at this. We are talking about when L of t is greater than or equal to 150. So if I were to draw in that line, okay, this is when L of t is equal to 150. Okay, if I were to find these values, you can see that in between those two values are the time when the L of t function is larger than the 150. So definitely I need to find those 2 points of intersection, and I'm going to store those in my calculator and find their values. So everyone go ahead, pause your video. You want to go ahead and graph this, and you already have the window that you should graph it in. Then graph y equals 150 as you're in your y2. Calculate those points of intersection and store them both, this first intersection point in A and the second intersection point in B. And then come back to me and see if we agree. Okay, so I went ahead and, like I said, typed L of t into my y1 and typed 150 into y2, and I calculated the points of intersection. I got these two different values for points of intersection. The first one I got was t equals 12.4283, and the second one was 16.1217. And those, like I said, came from calculating the intersection, second calc intersect. Okay, and then you can see here I wrote down that I stored that 12.4283 in for alpha A, and in for alpha B, I stored the 16.1217. Anytime I have these long decimals and I think I'm going to have to use them again, I want to go ahead and store those in, and that just makes it a little easier. Okay, so specifically it didn't ask when it was equal, it asked when it was greater than or equal to. So I could then take this information and say that now I know that L of t is greater than or equal to 150, clearly between those values. So between A less than or equal to t less than or equal to B. Okay, so now it wants me to compute the average value of L over this time interval. So what time interval? Well, from A to B. And so average value is average of a function. So the average is going to be 1 over B minus A times the integral from A to B of L of t dt. Okay, so go ahead, pause the video, enter that into your calculator, and this is where if you have it stored as a 12.4283 in for A and 16.1217 in for B, then this is going to become much easier. Okay, so you're going to go ahead and enter that in and come back with a value. And make sure that you also take time to think about your units of measure. Okay, so I got 199.426 cars per hour. Remember that when you are computing the average, your units of measure do not change. So if the original L of t was measured in cars per hour, then the average is also going to be in cars per hour. So keep that in mind because that comes up quite a bit. You want to make sure your units of measure match what you started with and then what the average is. We've referenced this before and we've made sense of it by talking about if I were to calculate my average speed while driving. Well, what do I drive in? I drive in miles per hour, and my average would be, say, 42 miles per hour. So my average speed was the same unit of measure as what my actual driving speed is. Okay, so let's move on to part C. Okay, this last question is pretty involved, and it is a 4-point question. There's only a part A, B, and C to this. Part A was 2 points, really straightforward. Part B was worth 3 points, and now the last one, this one is worth 4 points. So it says traffic engineers will install a signal if there is any 2-hour time interval during which the product of the total number of cars turning left and the total number of oncoming cars traveling straight through the intersection is greater than 200,000. In every 2-hour time interval, 500 oncoming cars travel straight through the intersection. Does this intersection require a traffic signal? Explain the reasoning that leads to your conclusion. Okay, so we have to definitely unpack what's going on here. Well, it's talking about this idea that the product of the total number of cars turning left, okay, so the product of the left, so number turning left, times the number going straight would have to be greater than or equal to 200,000. All right, well, what do I know? I don't know the number going left, okay, so I'm just going to put number L is unknown. I do know the number going straight is 500, okay, and so basically what I need to understand is that the number going left during a 2-hour interval has to be greater than or equal to 400. Now, this is over a 2-hour interval. Okay, this idea of a 2-hour interval is really important because what I want you to realize is that we're not talking about cars per 2 hours. We were talking about cars per 1 hour. This graph and this function is measured in cars per 1 hour. And so we have to talk about the number turning left being bigger than 200 per hour. If I need the number turning left to be greater than or equal to 400 over a 2-hour interval, then I need the rate at which they're turning left, L of t, to be greater than or equal to 200 because that's talking about a 1-hour interval. Okay, I need the rate per 1 hour to be bigger than 200 so that over a 2-hour interval I have more than 400 or more cars turning left. I hope that makes sense to you. All right, and then that helps us because now we have a graph and we have an equation for L of t. So now if I look at the line y equals 200, I can now do what we did a couple questions ago and calculate these intersection points where your L of t function is equal to 200. So go ahead, pause the video, do what we did earlier, and calculate those 2 points of intersection. Okay, so I'm going to pause for a second and come on back to me and with your points of intersection, with your times, your t values, and we'll proceed from there. Okay, so I found my t values to be 13.253 and 15.324. Now this is hugely important. The time that has passed between 13.253 and 15.324 is greater than or equal to 2 hours. Therefore, during any 2-hour interval of that time, those time intervals, they are going to have to require a traffic signal. Okay, so that's the concept that because there is more than 2 hours passed, so if this was 13.25 and 14.25, well, that wouldn't matter because that was just an hour, and so you wouldn't have gotten 400 cars at a rate of 200 cars per hour. But because there is a time interval that is greater than 200, that is greater than 2 hours, we can definitely say that they are required to have a traffic signal. Okay, so I would then make this conclusion. I would say yes, a traffic signal is needed or required for any 2-hour interval between t equals 13.253 and t equals 15.324 hours. Okay, so that was kind of an interesting, different type of question. I hope you followed with me. And that is a 4-point question. So, guys, I know that I've heard some of you say, oh, I'll just skip that one if I get to it. You have to kind of think through and don't just skip it. Okay, you have 15 minutes per question. So take your time, think through as much of it as you can, and process as far as you can get so that you can have an answer and you're not just leaving a whole 4-point question blank. Okay, that's it for tonight. Next time in class, we are going to practice another one of these real-world rate graph problems, and hopefully by the end of these 2 videos and these 2 days of classwork, you're having a better handle on these kind of big word problems that I know are scary, and when you face them and you take a look at it, you might feel overwhelmed. But hopefully you're seeing a pattern and a repetition of the same type of questions that are being asked, and you're starting to get more comfortable with them. All right, thanks a lot, and I will see you in class next time.